Hi, welcome. Can everyone hear me all right? Good stuff. I'm Alex Heneveld, CTO with Cloudsoft. I've got with me Alid Sage, who's our VP Engineering, and several of our staff dotted among the audience, including Andrew, who's done a lot of the work behind this. Andrew, you want to give a wave? So if you have questions as we go along, we're a small enough group, so please just interrupt us, but you can also ask any of us if you're following along. The topic is rolling out a high availability Cassandra cluster in multiple clouds, multiple availability zones within clouds. Some of the tricky issues that you hit when you start to use cloud in anger for real applications that you want to be reliable. The tool we'll be doing this is the open source project Brooklyn. So we'll start just with the housekeeping things that you can run in the background in order to follow along with the tutorial. You're welcome to follow all the steps. You're also welcome just to watch. While that's downloading, we'll do a background on what is Brooklyn, automated deployment and management tool. And then we'll go in. The first part of the tutorial, we'll all roll out a Cassandra cluster. You can target localhost, you can target your preferred cloud. And that'll be a hands-on session for those who wish to take part. We'll then come back and look under the cover at Brooklyn, kind of what's involved in the heavy lifting. If you want to do kind of serious complex stuff, kind of start programming the infrastructure. And then we'll come back and put that into action when we handle some of the wide area and high availability and availability zones issues with regards to Cassandra. And then in the last few minutes, we'll talk about what's next in the pipeline. It's an open discussion. This is an open source project, and we're very keen to have participants. So whatever your interests are, please feel free to raise them then. And if you have questions along the way, just give a wave, and more than happy to take them. So to start with the installing it yourselves, the instructions are all online at this URL. And if you just go to the main brooklyncentral.github.io page, show you the path to get there. Firstly, we're not going to use the M2 version. We will click on this link to come to the versions page, and we'll take the snapshot. Within that, go into examples, and in snapshot, you'll see a new example, which is the Cassandra cluster. And this has all the instructions that you need to follow along. Start just by downloading the binary distribution for Brooklyn. This little clipboard icon should copy it to your clipboard, so you can just cut and paste it. The % symbols will go away when you paste it, so it will work. And that will give you the base Brooklyn binary. The second step is to get the examples repository shown here. Then if you go into this directory in the examples, give it a build with Maven and a launch using the Brooklyn binary command. Just follow along with these code snippets, and that will launch the cluster locally or in your preferred cloud. So if you get all of the installs up to this Maven clean install, if that's working, by the time we come to the first break, you'll be in good shape to follow along with the first part of the tutorial. If you have questions along the way, just you can raise your hand. I'm sure you're not the only one, so other people would appreciate it. So summarize in brief, install Brooklyn, install the examples, set up your cloud, build, run it, and we can even do some stress testing. We'll kill some nodes and show that it is acting rock solid. The link will be here at the bottom for some of the pages, so that'll pop up periodically. So to flip over into what is Brooklyn, the backdrop to this, the problem that we solve, is that things keep changing. And whether it's new data sources, new types of infrastructure or infrastructure policies, things on top of infrastructure, platform as a service that's meant to solve all your problems, but you have to do things a certain way. Meanwhile, the infrastructure keeps changing. We get converged infrastructure. There are policies, compliance in big organizations, things that you have to do a certain way. Pretty much the only thing that possibly isn't changing is the expectation that your application stays on target and keeps working. Now, the solutions to these challenges, this constant change, exist, but they're scattered among lots of different experts. So the approach that we take is to try to provide a way that this expertise, this knowledge, can be encapsulated in a reusable, transparent way. And that's the idea of blueprints in Brooklyn. Now the blueprints, when we use them, have a number of nice features. They have push-button deployment. So with a single click, I can get it running on a bunch of servers with fixed IP addresses. You can also go into your preferred cloud or cloud environments, mix and match between them, and recognizing that applications aren't always built right the first time. You want a rapid round trip. We support localhost as a common location. Now you can set up a local cloud. I don't mean just VirtualBox, although that's supported, but just running straight on localhost, very lightweight push-button deployment. So first point to note is that these blueprints are very portable, and they're living in terms of getting the application running. But more than that, they're there to provide ongoing management. So the blueprints encapsulate the logic for looking after the application. How do we recover if things change? In some cases, it's easy. We just fire up a new node and magic happens. But more often, there's some orchestration. We need to coordinate the failover, make sure that the fixes are applied to various tables. If it's a database world, update load balancers. In some cases, inform other systems. We may have lost some transactions, and so we need to do some downstream reconciliation. All of this ongoing active management is included as part of the blueprint. So our vision is that applications in a cloudy world need to be designed so that they can run in all of the locations you want to be, but more importantly, how that application needs to change over time is now part of the application. Writing an architecture and filing it away as a Visio diagram is not good enough anymore. That kind of flies in the face of everything we now think in terms of Agile and DevOps. So Brooklyn is a way that within the application tier you can describe how your application should perform. In order for that to fly, it's got to be an open framework and it's got to be an extensible framework. So this is Brooklyn's an Apache licensed project on GitHub. If you go to brooklyn.io or brooklyncentral.github, you'll find all of the code, a wealth of examples, and then sitting next to it in the same Brooklyn Central repository and more in the Cloudsoft repository and others elsewhere, there are projects built on Brooklyn for deploying common applications, common types of systems. It's worth noting, part of the open source ethos is that you don't try to do everything. And Brooklyn's focus is very much this nexus of deployment and management. And to that end, when we're looking at server management, we will use best-of-breed tools for that. So we have close integrations with Chef, integrations with Puppet. Was fascinated to learn more about Salt this morning. There's another talk later this afternoon on Salt. So I think we'll see a good Salt integration coming up. Brooklyn is not concerned about how to set up the servers. It's quite happy for you to use the best-of-breed tools for that, and similarly, best-of-breed tools for monitoring. What we want to make sure is that all of these things are acting on behalf of the application, that there is a central design that is sitting there and that it can be checked in as part of the source code for the application. So by being open and extensible and understanding the systems that are used at all the different phases, the Brooklyn blueprints make the application's lifecycle transparent to all the stakeholders. So all the folks who had pieces of the solution from the first slide can see those solutions in the blueprint, whether it's editing the blueprint directly or looking at the runtime operations dashboard or a REST API and running their favorite tools, or feeding the data out and putting it into the preferred standard high-level dashboarding systems. So to kind of move on from the marketing and get to more of a physical architecture, looking at quite a complex application. This is a multi-tier app with a presentation layer, there's a processing layer, and then a distributed data store sitting at the back end, fronted by a GSLB DNS service in the front. a lot of applications will look something like this, running across two regions. Brooklyn lets you model this, and the approach to modeling is to put it into a hierarchical system like this, where the top level of my application consists of a web or presentation fabric, a processing fabric using something called Monterey, and a data store fabric using Gemfire in this case. Within those fabrics, I have clusters. Within the clusters, I have nodes. That is a common pattern, but it's not the only pattern. A cluster may be as simple as an autoscaling group. So in the case of load balancer with a bunch of Tomcats, it is effectively like an Amazon autoscaling group or a cloud stack tier. But other systems, and Cassandra is a good example of those, don't fit that pattern. The nodes are differentiated, and it's important that they're differentiated. More than that, you need to understand that differentiation in order to make sure that your data is set so that replicants are running across different availability zones. So that's a good example where we need to take the expert knowledge that sits on the one hand in the Cassandra community, scattered across a lot of web pages, about how do you actually build and deploy a system that will survive a serious onslaught of machine loss. So you need the Cassandra expert, but equally, to make it work, you need people who really understand the cloud infrastructure and networking. If you're going wide area, you'll experience pretty quickly that, well, the way Amazon gives you your private NICs in the cloud and the NICs you bind to is very different to the way Rackspace does it, which is different to the way other clouds do it. It's very nice. Some clouds will give you a fairly homogeneous fabric of networking, inter-route and soft layer being two prime examples, where you can have an private IP namespace in different locations around the globe that see each other. Not many clouds do that today, and so there are a lot of techniques, from standing up something like a virtual private network, Cohesive have some neat software in that space, through to rolling your own, or leaning on the public IPs if you're not too concerned about security. If you're coming from an enterprise world, there will be yet again different conventions and strategies and NICs and IP namespacing. On top of that, there may be maybe CEDAR and IP tables rules that you've got to apply. All of this knowledge needs to be brought when you're deploying an application into production. And so the blueprint comes to the fore in that at the high level, the application architect can think in these terms. But the people who understand, well, here's the way we set up a cluster of Gemfire or a cluster of Cassandra, they can supply the blueprint for that piece. And the one secret ingredient is that these blueprints are designed from the outset to be composable. So, of course, you pick up a blueprint off the shelf and you can reuse it higher up. Many of the blueprints, like clusters, allow you to kind of parameterize it going down the way, so it's truly composable, that I can say, well, I need a cluster, but I want a cluster of this type. So that's what we mean by the logical architecture. You see that there is a hierarchy. This view shows the hierarchy a little more explicitly. And down at the bottom, the purple things are mostly processes on machines. I can fake it by running them all on my laptop, and that's a great way to test it quickly. But some of them aren't processes at all. Some of them are services, like a geographic DNS. In Brooklyn's nomenclature, these are entities, and Brooklyn is ambivalent. A software process is a common thing that it looks after, but there's nothing special about a software process. So anything that needs to be modeled, monitored, and managed can be. But having this hierarchy of pieces lets you attach policies at the right level. And at the heart of Brooklyn is an event-driven, policy-based architecture designed around autonomic computing, so that we attach low-level policies down low. The management knowledge is near to the pieces which need it. So, for instance, we might have a restart policy attached to one of the processes. If it's a process on a cloud machine, I might have two restart processes, one that's restart policies, one that's restarting the process, should it fail, one that's restarting the server, if the server fails or if the process refuses to restart several times. Up at the cluster, we're probably concerned that the cluster's operating optimally. It's the right size for the load or the data or the combination. We don't assume in the policies that we know best. We've got enough scars that actually we know some things really well, but there are a lot of things, particularly when we start looking after advanced applications, that the application architects know. And in our view, scaling is one of those. Making sure that something is running at the right size is intimately tied to having the application-specific metrics that you need. In many cases, actually doing the scaling, both up and especially scaling back, requires some quite sophisticated orchestration. Cassandra, although it's getting easier, is still one of those examples. There are some best practices to scaling up and back. As you move up at a fabric, a wide area level, various policies come with Brooklyn. Follow the sun to optimize, place workload near to the consumers, or follow the moon, place it where it's going to run cheapest. In some cases, follow the data. If we've got some processing that's pretty easy to move, but it's working over different data sets, let's move it, transition it so that it runs as near as we can get to the data set that it's operating over. So you're not long-lining vast quantities of data, paying for it in terms of time and network bandwidth. So when you need to control every little piece, having that capability is great. One of the great things that started to happen in the last several years is that a lot of the middleware vendors now recognize that they need to do more than just give you instances and runbooks. Particularly in the realm of PaaS, we're seeing elastic clusters for Ruby, for Tomcat, for JBoss. Due to the way the entities are modeled is with object-oriented type systems and interfaces, you can pretty much swap out one of the web app clusters for a lot of the web-typey PaaSes. You get many of the same sensors and effectors, that is kind of metrics about what's happening and the operations you can do for the cluster. So for instance, a good example, some of these don't automatically resize, but they do expose a resize operation in exactly the same way as our load balanced cluster can resize just by starting up more and fewer Tomcats. So it's very much you control how much and which pieces you want to use. You mix and match these. The object orientation gives you a way to do that doesn't drive you insane over time. Coming back up to getting the application running, we mentioned at the outset that we've done a lot with portability. Targeting fixed IP addresses, targeting localhost are useful. Targeting a raft of different cloud environments is becoming more and more important. And I think that's where we, Cloudsoft as a company, have invested a huge amount of effort in the past 5 years. So that your application, these blueprints, are legitimately very reliable across a lot of different environments without making assumptions that we need a particular image ID in a region. It's quite happy to look, okay, we've got a relatively recent CentOS or Ubuntu build. These blueprints can work with that. There are also nice ways that you can describe as part of the blueprint. Well, if we're provisioning a new machine or looking for an existing machine, let's take one that has 8 gig of RAM. We're not specifying a hardware flavor or profile, but we're describing what we need in the language that someone who comes back later and looks at the blueprint will recognize. Yes. So all of that gave you agility, reliability, transparency, but you don't want to see that if it's working well. You just want it to work well. So the goal of Brooklyn, for most of us using it in a day-to-day, is that the bits that I just want to work, I don't have to see. And so the pieces here shown in green are the things that for this application, I think I want to specify. So I've said I want a web fabric. Here's my config for the DNS, and here's my WAR file. That's pretty much all I want to say. Everything that is, you maybe can see very, very faintly, I expect just to work. Now, when it doesn't work, I want to be able to go back, drill down, see exactly what went wrong. You have that transparency. But for just getting started, there's very little that you have to specify if you're reusing a blueprint. The same at the processing fabric and the data store fabric, and as you'll see when it comes to rolling out a Cassandra cluster, if you just want something that is reliable and high availability, those blueprints exist. If you then want to go in and tweak it and have very precise control targeted over which replicants, which data sits in which regions. All of that is possible. So this is a YAML snippet that shows kind of the minimum that you want to specify and how simply you can specify it. This is hot off the presses, by the way. It's based on an Oasis Camp standard deployment plan YAML. And it's currently in the Brooklyn sandbox, but you can check out the sandbox, run this example, and it will roll out a 3-tier application with the web app cluster and the MySQL node. Similar things for the application I just showed. The important piece here is that the config I care about is what I'm specifying, and there's very little that, if I don't care about it, that I have to specify. If you do want to control it to a much finer degree, that is fundamental to our design, so you can, but the important thing is you don't have to. This is all, of course, backed by Java code, so if you want to add new types, add new functionality, there are principled and testable ways to do that. At the level of software components, there's good tie-ins, as I said, to some of the server management, so you can reuse investment that you may have in various scripting from Bash through to Chef. So that concludes the first big part about what is Brooklyn. Before we flip over and do the tutorial, do we have any questions from the audience? Okay, Alad, over to you.
Sorry, let me just fight with the screen settings. Oh, does it? Oh, that's good to know. Wow. Cool. Okay, so I'm going to take a concrete example now of an automated Cassandra cluster. First of all, could I have a show of hands of who's tried using Cassandra? Quite a lot. And how many people are using Cassandra in production? Okay. So we focused on Cassandra here, but we also do integrations with various other NoSQL solutions, such as MongoDB, CouchDB, MarkLogic, and various others. But Cassandra has got a lot of traction, a lot of big customers using it. It's a distributed data store. It's very, very scalable and very performant. So, for example, Netflix did some performance measurements scaling up to about 300 nodes, and it scaled linearly to do a couple of million writes per second on their network, all testing in Amazon. And it's got excellent wide area support. So its replication both within racks or availability zones in the cloud or across different regions is extremely good and built in, and it will do things like monitoring the latency between various connections in order to tune things on the fly for where your data is being replicated and where you're reading from. And it's a table row store. So this slide here, which is very busy, contains a lot of information, but thoroughly recommend Googling for that and having a look at this. It was put together by 451 and gives an idea of where lots of different NoSQL or other database solutions sit together from different ways of looking at them. You can see the arrow there is pointing at Cassandra, so it's in the NoSQL zone. Its heritage comes from Google's Bigtable and also taking ideas from Amazon's Dynamo. And although it's just a tiny stop on this tube map of databases, it's actually got much more traction than many of the others shown here. So What I'm going to do is run some of the examples that you'll find online in our tutorials. So you can either work along now or at any point in the future. Please do get in touch. We'd love to have your feedback on that. Let me first jump across and show you. Oops. There we go. Show you some code that I'm going to run. So this is a blueprint definition in code. Alex showed you some YAML text file that ops guys could write. Hopefully you'll see the structure of this in code is very similar to what you could represent in YAML, but I'm a programmer, so I like writing code. In this blueprint, we've basically just said, I'd like to have a Cassandra cluster. Initially, let's just have one node in that cluster, and here's a name for it. And I'm happy to take all other defaults. So that's using the standard Thrift ports, JMX ports, and everything else. But what's important about this blueprint is that it hadn't said what location we're going to run it in. It could be on localhost, it could be on fixed list of machines, it could be on Amazon, or anywhere else. So if I now try running that on localhost, okay. Sorry, flicking the wrong screen. Okay, so the command I'm going to run is just to say Brooklyn launch the application simple Cassandra cluster, and the location I'm going to specify is localhost. So this is assuming that nothing is pre-installed on my machine. It will go out and download Cassandra from the official Cassandra website if it's not already in my local repository, which luckily it is here. Starts up the process. In this case, it was just one node, and therefore it doesn't need to wait for any others to join the cluster. And through our web console, we can now have a look at that running. So our cluster has a single node. We've connected to it to retrieve a whole bunch of metrics. And what I'd like to do now, though, is to make it a bit more interesting by running one that's going to actually deploy it onto a cloud. So this is going to take a while to run. So I'm going to kick off the command first. This is actually going to run the next demo I'm going to show you, the high availability Cassandra cluster. But what's important here is I'm specifying a different location. So I've set up this AWS EC2, and I've tuned the configuration to say I'd prefer to run this on CentOS. And now if we load that page, we'll see a bigger cluster is now being deployed into AWS. So there's a few more lines of configuration in that code, but before we drill into what exactly that's doing, let's take a step back again and look at how Brooklyn is modeling these entities, wiring them together, and what these various configuration options mean.
So I'll give you a sneak peek of the code that you can write to have full control over it. I'll step back from this and start with a little bit of the theory. We mentioned autonomic management. That hierarchy that's there, it's not strictly enforced. There can be cross-communication, but having that hierarchy makes it very useful to see at the high level, what do I care about? Is it healthy or not? Maybe what's requests per second or load like? But when I'm drilling down, whether to understand performance, see how a test went, or diagnose a problem, being able to navigate and pinpoint exactly an individual node, an individual task, and see those metrics becomes very important. So at the root of this modeling approach to autonomic management says that we have a managed element is anything which emits some events, sensors, I can see how it's doing, and has some effectors, operations, things like I can tell it to do. A managed element can be paired with a manager, where the manager will monitor the sensors, analyze, create a plan, and then in some cases execute that plan by invoking effectors going down the way. Or in other cases, it may escalate some situation, say, I can't solve this. It's not complicated, it's kind of an obvious starting point, but we see a lot of approaches that sort of say, well, let's model everything with precondition action. And if you take a precondition action, you lose this essential building block to a model that gives you something to work with and understand over time. So conveniently, an autonomic manager can be another managed element. So it will emit sensors and effectors. And that allows you to build up interesting hierarchies where at the root might be a high-level dashboard type view of the application, but then down at leaf nodes, I can have as much detail buried away as I need. As an aside, it also provides a nice route to distributing this, carving it up and federating it. So to come back to a very simple example, let's take a three-tier app with a load balancer, some app servers, and a database node. There are a lot of approaches that deploy quite nicely this type of application just using scripting. And if something is quite static and doesn't need to be portable, then scripting is a good solution. But when it comes to wanting, instead of scripting a solution, but to bring programming and treat it as a computer science task, let's actually put some good discipline, software engineering behind the application, our technology comes in. And it starts to occur when, well, we need to specify an autoscaling policy at the cluster level. But of course, whenever we do some autoscaling, well, we need to update the load balancer. And there's some subtleties which are a bit niggly. You can solve them, of course, but let's not update that load balancer until a new app server's online. And actually, let's wait until our application has kind of prefetched its cache and the application itself is ready in that app server. Don't just add it to the app server as soon as it comes up, because that's asking for trouble. Similarly, if we're taking something offline, well, we could just kill it, but a customer who's got a session connected to that machine probably won't thank us for it. So let's kind of prevent him from being available for new sessions, and then when all the sessions have terminated, let's take him out of the pool, and then when any processing or writing to disk is done, then we can safely and cleanly tear down the node. You want things to be reliable and resilient in the case of failure, of course, but you don't want to take advantage of that by just killing things crudely as a matter of course. And finally, kind of one of the pieces that often gets buried and has some fairly messy solutions in practice is the need to inject the location of the database into the app tier. And there are a host of conventions. If you go to Cloud Foundry, you'll be asked to do it one way. If you go to OpenShift, you'll be asked to do it another way. If you go to App Engine, you'll be asked to do it 3, 4, and 5 different ways, depending what language bindings you're going after. And if you're dealing with an application or a design pattern where you've got the conventions that you like for injecting that information, why change? You probably don't want to move to if you've been working with an environment where you can update that database address while it's live by poking a REST endpoint, you probably don't want to move to a simple model where the database has to be set as a JVM system property or an environment variable in Python. So you want ultimately, in many cases, control over how the dependencies get injected. You also want to be able to see those dependencies and understand those dependencies in real time. There are some nifty solutions that lean on DNS for doing that. DNS is fabulous. It can solve a whole raft of problems. But you're building in a whole DNS stack in order to make your application portable if you go down that route, which also probably isn't what you want, especially if you've kind of bought into lightweight, agile, fast deployments. So in the Brooklyn approach, we have the same piece parts, we call them base level entities, or concrete entities. And this is where, when we go into the field, we tend to reuse the scripts and the solutions that people have. But where people have kind of nice tactical functions for setting up each of these piece parts, scripting often gets messy when you're dealing with injection of the database into the app server and the app servers into the load balancer, especially when that's starting to change over time. Brooklyn's policy architecture leans on the event-driven system. The sensors coming out of it drive policies, which drive logic. You can pick a lot of policies up off the shelf. In fact, if you take a controlled cluster of any variant, that automatically has this little targets policy. The targets policy is very simple. He's monitoring the targets, waiting for them to say that they are ready. Ready doesn't just mean the machine is there or the app server is started, but that the application's running. And it will track these active targets and make sure that the load balancer gets updated appropriately. The Autoscaler policy is the more interesting one. This is where we are saying, well, every cluster has a resize operation. That in the case of JBoss is pretty simple for resize. In the case of Cassandra, resize is quite a bit more elaborate. The Autoscaler policy is kind of orthogonal to that. Anything which is resizable can have this policy attached, and you can tell it to monitor any particular sensor metric. So if we care about CPU in a kind of a common, pretty dull case, we can aggregate the CPU or take some normalized metrics or kind of look at the 90th percentile and use that sensor to feed into Autoscaler. But if we have an instrumented application that's telling us something more application specific about its behavior, how many views is it running? How busy does it think it is? We can use that metric to drive autoscaling. As we come down the way, there are a number of different plug points where you can customize. So we can plug in different drivers for, we've talked about scripting in order to get things running. Monitoring is another one where we can connect directly to JBoss over REST, or if it's JBoss 6 over JMX. But equally, if you've configured it to talk to a monitoring system, that monitoring system can then feed back into a database, and Brooklyn can feed the database and triangulate this information. Equally, it can coordinate that information with views of infrastructure behavior and network behavior that might come from a virtualization. All of this information can sit within that one entity and be available to the policies for making the right decisions. Finally, as we've said, in order to make that blueprint run, we add a location or set of locations. For the ones shown here, they're all operating system containers. That's the level of abstraction we care about. They can all be the same operating system container, or they can be cloud machines or LXC. The important thing is that from the top level, the structure of the blueprint and all of the management logic remains the same. So let's come back. This is the cluster of what we'll build. I'll now go kind of 2 levels down and return to some code and show you the piece parts so you'll understand exactly what Alid was building up. So in the top right-hand side, we'll build up to this blueprint we just saw. You can start by defining an application or any entity by declaring a new class. And then within an init method, we say what we want to do. The YAML will build this for you automatically, but if you want to put in some complex functions or closures or policy logic, add new sensors, code is the place to do it. Here we're just taking a single JBoss 7 server. I'm adding a child, the spec is JBoss 7, and I'm setting one configuration, which is the root var, and I want that to come from a config parameter, the var path. If you're on our website, this is the simple web example. It's the first of the tutorials on our website. And so someone can supply a var and I will run it, or I've set a default, which is hello world in the stock example. I can add additional configuration, like setting the HTTP port, And in this case, I've set it to 8080 plus. That plus, as you might expect, gives it says, I'm going to allow you some flexibility. If I've got a new cloud machine, I would expect to get 8080. But if I'm running this on localhost and 8080 is in use, it'll try 8081, 8082 until it gets something running. And it will tell me back as a sensor what port it's running on. You can do the same thing, bring in a MySQL node. So I'll add that child. So at this point, my application consists of MySQL together with a JBoss server. And I've configured the database to run a particular initialization script. But what I've not done, crucially here, is told the app server anything about the database. And as I've said, we're agnostic about that dependency injection mechanism. We support a lot of different ones, from environment variables to Spring, to poking REST endpoints, to updating database keys. But a common one is to pass in for Java app servers to set a JVM system property. So in this case, it's the 4 lines at the bottom, which is quite a lot, but Java's a verbose language, so we forgive it that. The pieces of what it's doing are relatively simple. We're configuring a Java system property, Brooklyn example, DB URL, and we're going to set that equal to a formatted string, which is a JDBC URL with a user and a password. The only thing that's quite unusual is that we don't yet know the address of MySQL. So the mechanism for resolving this, of course, is to lean on the sensors that Brooklyn will emit. One of the contracts of the MySQL node is that it will publish MySQL URL when it is online, when it's finished running the initialization script. Attribute when ready simply says, well, let's wait until the MySQL entity has emitted its URL sensor. Now, under the covers, what happens is that that becomes a Java future. It's a task stored in a map. Format string, in turn, will be a future, which is blocked by the underlying future. And that system property is containing that future in the map. That means when we run this, the 2 nodes can start. It's not blocking initially. It will provision the machines. It will install the software. Everything can quite happily run in parallel. It's only when JBoss needs to start and needs to have his JVM system properties that it will look in the map and say, this value is a future. Let's block until that future is available. If MySQL finishes first, which it often does, that future is immediately available. The right value of the MySQL endpoint gets injected. If, on the other hand, it changes over time, and we may see this in some of the Cassandra examples when we do seed populations. If some of the seeds go away and we get new seeds, the address of the seeds needs to change. Those sensors will take the current value at the time of running. Next, there's one small change in the code to go from having the 2 nodes, which have a connection, a dependency injection, to having an entire cluster at the right. And if you look where we said JBoss 7, we've now asked for a controlled cluster. It's actually the controlled dynamic web app cluster. And each of those tells us something about what it's doing. It's controlled, means it gives us the load balancer. It's dynamic, meaning it allows us to resize it. And it's web app, meaning that it will give us a URL. It will aggregate certain common web app metrics across the constituent pieces. So it will, for instance, tell us average requests per second, mean latency, things like this. And at this point, I can deploy it, and I have my targets tracker policy as standard with the controlled cluster. And we have an application which we can manually resize. We can run it in just about any cloud, and we can run a WAR file that's consuming a database. We may not want to go with the default of 1, kind of defeats the point of having a cluster, so let's set the initial size to be 2 for this blueprint. Of course, because it is code, you can make that programmatic. If we're running quick sanity test on our laptop, then make it 1 or skip the cluster altogether. But if we are trying to run some stress tests, then bump that up to 10. When we go into production, maybe there's some extra steps that we want to tell it to run about locking down the environment. coming back, all of this can be done through the declarative format. So this is the exact same blueprint specified in YAML. That means that if you're facing off to ops guys, to people who don't want to write code to manage it, it can all be described at this level. If people are working at it within a context where they more naturally would program, like Alid, where they want to run lots of automated tests against it, then you can drop down to the heavyweight environment, which is Java. Finally, a couple other kind of examples of code snippets. It gets interesting when you're adding in your custom policies for resilience, for elasticity, for wide area optimization. In order to make that work, you need to start with the more mundane things about making sure we get the right information. So we started with the first 2 lines. That's just the code to build us our model. In this third line, where we add an enricher, we're actually telling it, well, compute latency, go against the URL sensor that the cluster will publish, and take 10-second roll-ups. So we get rolling averages of the latency against our cluster. And that will get published as a sensor attached to the web tier. We can then add a policy, and we'll add the autoscaler and we'll attach that to the web cluster. In this case, let's look at requests per second, keep it in a given range, but also let's put some caps on the size and attach that. And then finally, let's bubble up a couple sensors to the root node so that if all we want to do is have populate a simple dashboard, I can just go to the root of this app, get a handful of sensors which I can drop into my preferred dashboard. So that concludes the second part of the theory behind Brooklyn, and now I'll pass back to Alid to show some of the same ideas and how they've been applied to automating Cassandra.
Thanks, Alex. Okay, I just need to stop this having 2 displays because it's far too confusing. Okay. So we have what I call the high availability cluster that consists of 6 nodes running in AWS. And before we drill into the code for that, let's pull out a few things, relate them back to what Alex just said. So we have some sensors for each node. And for example, we might be pulling out from JMX some read metrics. So far we haven't applied any load to it, so the number of active and pending and completed reads to the Cassandra node are currently 0. We've also added some enrichers, so some ways of aggregating this information. So for example, we look at what is the average number of requests that are hitting this node in the past 10 seconds, but on average here. And we aggregate all of this at the cluster.
Command minus.
Yeah. Yeah, that's better. Cool. Okay. So let's pick one of these nodes and we're going to go into that node and we're going to apply some load. So, yikes. Too many windows. Where's it going? Here we go. Okay, so this is using the standard Cassandra stress tool where we're firing a bunch of insert requests at that node. And if we now look at that node, we'll see that, well, it's finished those writes, so, and we've got a measure of of how many that was doing, and we aggregate that information at the cluster level. Whoops. It was too fast, so we're back down to 0. Okay. Let's jump back to the code and see what other configuration we had in there. Right, so going through each of these lines, we said that we'd like to have 6 nodes in there, but what we're interested in this demo is high availability. So we want to spread this across availability zones. So I ran this in AWS, giving a bit of background for what that means. Amazon divides up places where you can have your VMs into regions. So this could be in Ireland, in US East 1, in US West 2, and so on. Within each region, there are then a set of availability zones. You can think of these as separate buildings that are then clustered together, very close to each other, with extremely high bandwidth connections between them. But each of these individual buildings will have shared power supplies, shared networks. And periodically, Amazon have availability zones going down for a few hours. So if you want a high availability application, you must spread your application across availability zones in a given region. So here we've said, please spread those across those availability zones, and I'd like to spread it across 3 by default. We've also set up some Cassandra configuration, and at this point, I need to flip back the slide to say what this Cassandra information means. Okay, so 5 minutes on what Cassandra is doing under the covers. So Cassandra is a distributed database. This means that if you store a key of information, it could be on any of those nodes and replicated to some other nodes. So if you want to be able to get that data back again, you need to know which node to go to ask. Or more specifically, you can go to any node and it needs to know where to route the request to get your data. The way it does this is by dividing the world of data up into a ring. So here it's represented from 0 to 100. In real life, it's 0 to 2 to the power 128. And each node is given a token. So it generates a number which gives it a place on a ring. And then when you compute a hash function on the data you want to store, so for example, if I'm going to store some data, I'll compute an MD5 on that data that's about to be written. And that tells me where on this ring will my piece of data be. And then you just look at which node is responsible for that section. So you basically go clockwise from a given node, and that tells you which node is going to be responsible. So for example, if my hash function says that my value is 10, then that's in the range from 0 to 25, so I need to go to the node with token 0. So any node can calculate this and know where the data is stored. Obviously, we want more than one copy of it. We want to have replicas. And the default strategy for Cassandra is just to store it on the next few nodes in the ring. So if I set my replication to 1, it will store it on the next one after the one that's actually the master of this data. And therefore, if the first one goes down, I still have a copy of my data. So to add in a few more nodes there, what we'd like to do for high availability is to consider the physical location of these machines. So Cassandra describes these as data centers and racks versus Amazon's description of regions and availability zones. But if we think of it as we'd like our data to be on separate racks, then what we'd like to do is if our data is stored at R1, we'd like to replicate it on R2, R3, and R4, and we'd like those to be on alternating racks so that we spread our data across as many racks as possible. And therefore, if one rack goes down, we still have the data available. So similar idea with data centers, except what we'd like to do is to make sure we have the same number of replicas in our local data center and also then ask the other data center for however many replicas we want it to have. And if it has racks as well, it will spread its replicas across those racks. So to put that into practice for, if we have here a couple of data centers with a couple of racks in each, and a client comes in, the client can connect to any node in the Cassandra ring and ask it for any piece of data. That node will then work out who has the data and who the replicas will be. And depending on the consistency level you want, then it needs to ask a number of these nodes for the data. So on the right there, you can see different consistency levels we could have. If we have a consistency level of 1, it means we just want the data from any node that has it. So we could ask all 3 for it. The first one to give us the data back, we'll believe it and use that data. If you want to make sure that you're getting more consistency, then you might say, I want a quorum. So if the data's been written to 3 nodes, then I want to wait until 2 of those nodes come back with the data, which means that if we're doing that for writes and reads, then we're going to have more up-to-date information and be able to tell when it's changed. There's also some options for local quorum and each quorum, which relate to when you're running across different data centers. So with different data centers, obviously we want to limit the amount of traffic that's going between these 2 data centers, and we don't want every read to require waiting for some wide area communication. Local quorum is a common configuration that people use. And what that means is when the client reads the data, just ask the nodes in the local data center. When you write the data, then it may well block until the data has been written to that local data center, but then it writes to the other data center asynchronously. So here, the client has asked that node 10, which is then sent it out to our local nodes. It's also sent it to an equivalent node in the other data center, which is going to replicate to its nodes as well. So we now need to know how to configure Cassandra so that it gives us the desired behavior. The thing which we need to think about is the snitch, as Cassandra calls it. So a snitch is a way to figure out, given an IP address, what is its physical location? What's its IP address? What rack is it? What rack is it in, and what data center is it in? So we can make a sensible decision about which replicas to use. In the demos we're showing just now, we're actually making use of 3 different snitches. So those are the ones I'll focus on. The simple snitch just says, I don't care, just write it to any, if we have a replication of 3, write it to any 3 nodes. And that's the one I used when I was running on localhost. The gossiping property file snitch says that let's write a property file that says, here's a node, here's its rack, here's its data center, and now please gossip and tell each other about it. So as these messages get exchanged, then all the other nodes find out about the rack and data center that they reach in. The next one, which would be fine if we were just running an EC2, is the EC2 multi-region snitch. Now, what this does is it allows us to deal with problems of should we be using private or public IP addresses. So if you want to talk to something in the same availability zone, or sorry, in the same region, you need to use a private IP. If you want to talk to something in a different region, you need to use a public IP. So when do you use one and not the other? It depends which node you're talking to. And this EC2 multi-region snitch copes with that by looking at who you're trying to talk to. Does its data center match? If it does, let's use the private. Otherwise, let's use the public.
Before you go on to the last one, which is the neatest of them, someone's notified us that the examples repo was running a slightly out-of-date version of Snapshot. So that's been updated. I think some people may have figured out that they can get the examples also from the Brooklyn repo, and there's an example subdirectory, which is always current. But if you did hit some glitches cloning the Brooklyn examples repo, following the instructions, that should be fixed now. And if it's not, or you've got any questions, just kind of wave your hand and point at me or Andrew. I'm more than happy to come and kind of work through niggly issues with the rollout and environment setup. Back to you, sorry.
Okay. But the other demo I want to run is one where we're going to run across multiple cloud providers, so across Amazon and Rackspace. But pick the two of your choice. We use JClouds under the covers to talk to a range of cloud providers through this common API. At that point, then, we can't just rely on using the Amazon mechanism to find out what the public and private IP addresses are. So I needed to write my own multi-cloud snitch, which allows a control plane to actually configure the node and say, here's your private address and here's your public address. And then, other than that, it behaves very similarly to the EC2 multi-region snitch. But from the point of view of this demonstration, now that that's written, we can just make use of it. So jumping back here, we're still at the point of the high availability cluster, so everything's running within the same region. So we can use the gossiping property file snitch. In other words, we can rely on everything seeing everything else's private IP address. We've added some more configuration options, though. Because we're interested in high availability, spanning availability zones is the first step, but also we want automated policies that are actually going to respond to node failures, processes failing, and so on. So if we look at these lines added here, we've said that the member specification, so in other words, for every member of the cluster, then we'd like to create an entity of type Cassandra node, and as well as all of the default ports and everything else, we're going to add in some additional configuration of saying, please run with a service failure detector policy. Now, this policy says, let's look at whether we can contact that node, what state do we expect it to be in based on is it starting or stopping, so does it look like it's failed? And if it has failed, it's going to emit an event of entity failed. So the next level is then to wire up a service restarter policy. And this is working at the process level. So on the actual machine, it's then just going to restart the process. However, we don't want to keep on doing that, because if the machine really is unhealthy and it keeps on going down, we need to escalate this. So the default configuration of the service restarter, and again, all of this is configurable, is that if it fails twice within 3 minutes, then let's abandon that and we'll raise another event of entity restart failed. And that allows us to plug in another policy, this time at the cluster level, of a service replacer. So if we fail to restart this process, then the cluster is going to say, I will start a replacement VM, install Cassandra and set it all up, and once that's ready, I will take down the old node. So let's see that in action. So on that machine that I logged into before and ran the stress test, I can find the Cassandra process and kill it. So if we're looking over here, we can see just now all the nodes are healthy, but once I kill that, then this one is now doing some activity, you can see here. And if we drill into its activity, we can see a restart is in progress. And we can drill into information about that task.
If you keep going, you can see the standard input, standard output, all the details that you would want to know in the wild.
Yep, but what I need to do as well is kill it within the next 3 minutes to make sure that we then decide this node really is unhealthy. So let's find out the new PID of that process. And what we expect now is, you can see this thing is now on fire. The node is considered unhealthy, it's not worth restarting it there, and down here we can see another node is coming up.
And that's because the policy was configured to allow one restart within a time window, but not two failures.
Yep. Okay. The other thing we could do is to simulate failure of availability zones. So to do that, what we'll want to do is, given I'm going to do this via killing processes, I don't want it just to restart them, so I'm just going to go through and suspend each of these.
While he's doing that, there's a little tab in the top right that says script. And don't expect you to go and continue with what you're doing. But in there you can find all the details of the REST API. This is just a JavaScript GUI that's driving the REST API. So it's very easy to script this type of task. That's the one that's on fire.
Yeah, I was going to... It's also the one that I wrote the data to, so... yeah, what I was going to do is to show that that data is still available once I kill 2/3 of the nodes. But in the interest of time, I'm going to just push on just now and make sure we've got time to show the wide area one. So here's another application I've launched. And this time, we can see that we have an AWS and a Rackspace subclusters that combine together to form a cluster. And we can see the live node count is 4 for the spread across here. And we can see the data center, US East 1, rack name US East 1B, and similarly for Rackspace, the rack is London, and data center Rackspace UK. So to launch that, we have quite a similar looking blueprint here. This is where the snitch comes in, where we needed to specify a different snitch, so we specified the multi-cloud snitch. And because this is needing to be pull requested and put into Cassandra still, then I needed to upload that. For each of the Cassandra nodes, we've set up identical policies there. So the only difference really, other than the snitch, is then at the point when we start it, that we're going to specify 2 different clouds. So AWS EC2 US East and Rackspace UK. So if I launch that, we'll see that one starting up, but this will take maybe 10 minutes. So let's flip back to the one that I started earlier. So with this one, let's simulate, so not just failure of an availability zone, but of an entire region going down. So this is where I geek out a bit and start running lots of scripts. So if we find out and a host,
can you also do it in the Amazon console?
Yeah. Crazy number. that's gone. So I'm going to have to change my mirroring to get that command back. Do you want to say anything while I do this, Alex?
So this will be similar to the demo that we started earlier, running this standard Cassandra tool that will populate some nodes with a bunch of data. We'll start by populating a node in Amazon. Once that's done, we will go into the Amazon console and we'll kill all the nodes we have running in Amazon. We'll then see the policies respond by restarting nodes in Amazon. And the litmus test will be, will we find our data when we go back to the new nodes in Amazon? Now, if that happens, of course, what we can conclude is that the data was replicated as we expected across the wide area, in this case, availability zone into the rack space, and that it was copied back. And that kind of in orchestrating that is, I mean, people set it up manually and have kind of complex diagrams so that they know where their availability zones are. But it's very easy to make mistakes. It is the kind of thing that is rife to be automated. And so what Alan and Andrew have done is set it up so that it is automated, and it's automated in a way that's smart, using the right snitches, whether you're in Amazon or Rackspace, and doing the right thing if instead of wanting wide area failover, we want to work with availability zones or pods in CloudStack or Amazon or pick your poison. That get launched from the Amazon machine.
Oh yeah, sorry. Thank you.
Richard.
The Cassandra scheme that's on the screen there, whereas the web has to have an engine next to it doing the load balancing, there doesn't seem to be an equivalent for Cassandra. Is it the thing that you're able to query any single individual node in the ready node, or will be able to provide the answers you need?
Yeah, that's a good question. Yes, it is, but you need to then consider about which nodes have you told your application about. So you can give it multiple nodes that it could then talk to, so that if one of those fails, it can then go to the next one. So in terms of load balancing, it's not a problem, but in terms of single point of failure for your application not knowing about who else to talk to, it is a consideration. And things like the Netflix client has provided support for being able to supply lots of host names, but really, if those set of hosts change, you then want to dynamically inject the replacement host IP addresses.
But kind of in terms of, there's a kind of common pattern of, okay, there are some routers and then there's the content or the leaf nodes. And in Cassandra, everyone acts as a leaf and has sort of a piece of the elephant, some of the data there. But everyone also has a piece of the routing table. And so it may have some of the data you want, but more often it won't, but it will know who to contact, who does, or who can point you to the right place. So that's that architecture. There are a bunch of different architectures for the different NoSQL and NewSQL schemas. Kind of Alan put up earlier that sort of why Cassandra's interesting. Okay, they all say that they're scalable and performant. Cassandra is one of the few things that legitimately claims to have good wide area support, and that there's a very thorough model of understanding different regions, both at the rack level or availability zone level, and also wide area. And you can understand it. If you're setting up replication policies, well, some tables, things that change frequently and have lots of data, but it's not time critical, well, let's keep local replicas, but let's not pay the costs and chew up the network, ensuring that all of my movies are copied across four continents. But if we come to transactional data, then absolutely we need that. So on a kind of per table basis, you can set up different replication policies. And so that fine-grained control, both at the data and at the locality, is one of the reasons I really like Cassandra.
Okay, so finally managed to find the right commands to run. So what I've done is I've written some data to US East, and now what I'm going to do is to turn off those policies so that I can simulate a failure that we can't recover from. And now I'm going to kill an entire data center.
Yeah, and you're doing this at the process level rather than at the VM level so that we can restart it more quickly without waiting for Amazon to provision all the machines.
Being quite slow. Okay, while that's running in the background, let's jump on and say, yeah, we're very keen for folk to have a go at this themselves, look at the Cassandra tutorial, work through those examples, everything, all the code is online, feedback much appreciated. We'll be writing additional tutorials for other NoSQL integrations that we have. So if you have a preference of those, then come and talk to us about that and tell us what particular use cases you're interested in. So I'm going to spend some time talking about some things that are difficult about doing this with Cassandra, or in general, writing blueprints for applications that will work multi-cloud. So the first thing was the multi-cloud snitch. So that was reasonably straightforward. When I accepted that I needed to write one myself, I could just take what they'd done for EC2 and write one that would allow me to supply the configuration so that a control plane could really manage Cassandra. But even once I'd done that and then ran it on AWS and Rackspace, then, as Alex said, different clouds have different configurations. So for example, Rackspace, you have 2 NICs in each VM for public and private, whereas Amazon, you have a single one, and it just looks different for a different IP address depending on whether you're inside or outside. So just taking the same configuration and running it on 2 different clouds will not necessarily work. So you need to then look at how best to configure Cassandra to work in each of these different places. Also, looking at making this work properly for the high availability leads to the complications of the seeds. So, taking a step back, in Cassandra, the seeds tell it which nodes to talk to. So if a node wants to join the cluster, then you supply it with the address of other nodes that it will then attempt to contact so that we can ensure that they all talk to each other. And what you definitely do not want to happen is for some nodes to talk to some and other nodes to talk to others, and you end up with a split brain where you have 2 separate clusters that don't know about each other. So in the simple case, it's pretty straightforward. You just tell all the nodes to have the same seeds, and they all start up. But if you're dealing with something that's a bit more dynamic, the addresses you gave those first nodes those machines may have failed and been replaced. So the set of seeds has therefore got to be a lot more dynamic, and you've got to be quite careful about updating this list as nodes are added and removed to make sure that you don't then get nodes forming their own subclusters. Also, if you look at the Cassandra documentation, it then gives recommendations of like when you start a node, then wait 2 minutes before adding another node. So timing is an issue when you're automating things. And the first pass at automating this, there would be non-deterministic failures because obviously we didn't want to wait 2 minutes when we were automating a bunch of tests. And gradually we'd increase that time until it became reliable.
That's been an issue with kind of almost every software that we've looked at automating. When you work through the steps in a runbook manually, if it's a complex deployment, it usually works, depending who supplied it. When you come to automate the same steps, you find that, well, actually, step 4, you've got to wait 20 seconds afterwards, or you've got to wait for the database to be online and populated. There are implicit delays that are sort of assumed, and if you're typing them, they always happen. But when you come to automate them, they don't. And one of the disappointments I had with Cassandra was that it suffered the same issue. It's gotten better in the more recent versions, but some of the even kind of versions from several months ago, there's sort of inbuilt assumptions about how long you wait for the quorum to be established and for them to become in sync with each other. It might look healthy before then, but if you try to write data, it will come back with a kind of scheme is inconsistent error. Digging into it, you can usually find out the reliable way to determine if it is ready for use. And so that's a useful thing to bake into the blueprints, that nowadays if we encounter something like this, we don't advertise that service up sensor until we actually know that those initial calibration steps are completed. Where things are independent, you want them to run at the same time, but quite often there are joins that have to be said. So just being able to say, oh, by the way, don't start the leaf nodes until we know that the aggregator has emitted, at least 3 of the aggregators out of my pool of 6 have emitted service up. Being able to put that into a one-line function call as part of our deployment, and then by extension having it in the YAML, makes it very powerful to make those kind of these complex real-world dependencies easy to work with and live with. Someone's got to go through the pain of figuring that out, but if it can just be one person and reused after that, it's a much happier situation than all of us getting those scars.
Yeah, and it's worth saying that the Cassandra documentation is very good for this. Not necessarily for saying what will be the gotchas when you automate it, but saying all of the steps required to do things like adding a new node or more generically increasing the size of a cluster is well documented. And then turning that into actual code that in a DevOps way can be run is certainly our aim. Also, we're keen to focus on the cloud abstractions. So you saw there I ran across availability zones in AWS. So some clouds have that concept, some don't. And ensuring that we provide a common API that allows you to query the availability zones that exist, pick the ones you want to run, that you want to use, and spread your nodes across them is work in progress to expand the number of clouds that we're giving support for. And there's similar abstractions that we're doing for volumes for if you want to work with Amazon Column, Elastic Blob stores, and so on.
So on that, if anyone is looking at running Cassandra in OpenStack or CloudStack, we would love to work with you to make sure that we bring those availability zones into the same kind of snitch implementation inside of Cassandra.
Yeah, or more generally, other applications that you want to spread across zones in CloudStack, OpenStack, then the same generic solution applies for other clusters that are resizable to ensure nodes are added across the different zones. So next things that we're looking at there include adding additional capacity. So as you add nodes into the cluster, there are multiple different ways of doing this within Cassandra. Where it gets tricky is if you want to maintain balance across the nodes to ensure that the keys are going to be spread evenly and therefore the load is going to be roughly even. So how do you choose the tokens to use? How do you ensure that as you add the nodes that you do this at the correct times? And how do you run all the node tool move and clean up operations to ensure that the data ends up on the new nodes that you've added? There's lots of other scope for automating other things, like you're supposed to regularly run routine node repair and do this during quiet periods and do it at one node at a time because it's extremely CPU and disk intensive. Other things that we're keen to do include being able to add a new data center on the fly. So this is something which we've done for other applications, such as an Open Gamma demo, which Ask us about afterwards. So there's various steps that are documented that need to be automated in order to add that cluster in and ensure all the data gets replicated to it. Similarly, taking snapshots for backup and so on are all vital for truly high availability. Just going to see what... Not sure what's going on for my script there that was going to be killing those nodes.
Console.
Okay. So
You can also just do AYSO, the ID.
True.
Or is it 5.0?
Okay, so once those processes stop responding, then we'll see those that cluster go on fire. But what's important is that we set up the data center name within the Cassandra configuration so that Cassandra knew that these two nodes were in one data center and these were in a separate data center. The other thing worth noting for Cassandra, if we go back up to the command that I ran to write some data, so it's at the point when you write the data that you decide what the replication level is for that particular key space. So different pieces of data could have different levels of replication depending on how important it is. And similarly, when you retrieve that data, you make decisions about do you want to just ask for the first node that gives you the data back, or do you want to ask for the quorum to ensure that you've got the latest writes, and so on. So for this data, I said that the replication strategy was to be the network topology strategy, which in other words will look at which data center and rack each of these nodes is in. And strategy property, I told it in the data center US East 1, I want 3 replicas, and in rack space UK, I wanted 3 replicas. And that will automatically then try to spread those 3 across racks within that data center, but it will also ensure that those 2 data centers both get the data. So if I now were to go into the machine in AWS, in rack space,
from your Amazon machine?
Yeah, let me grab that.
Should do it from the Amazon host.
Oh, sorry, yeah. Yeah, again. I think I must have dropped the connection to it then. So at this point, I can now run a symbol command that will read out that data. And we can see that it retrieves all 1,000 values. So if I just set up a replication that hadn't told it about the data centers, then we'd have expected a random distribution of replicas for the different keys that had been written, and therefore some subset of that data would have been lost when we killed half of the nodes. So that concludes my demos of Cassandra.
So it was a little anticlimactic, I think, just to see that one number, 1,000. But if you turn off any of those, or you kind of run through the same steps yourself, even following the run book, you probably won't see 1,000. You'll be lucky to see 800. Once it's like all of these things. Once you understand all the moving pieces, it's not that hard. It does make sense, but there are a lot of moving pieces to understand. And if you just want a reliable deployment, you don't want to have to know all those moving pieces. Now, one of the answers is we'll just use Cassandra as a service. Find someone who has it. But for the vast majority of applications still, they're not being offered as services, and actually they're certainly not being offered as reliable, cost-efficient services. I think that will start to change, but it will always lag behind the state-of-the-art of the software. So if you want to use kind of Yarn type recent deployments, or Cassandra 2.0, or kind of sit with more recent patches. Bearing in mind many of these are successful because they are in the open source. People like the fact that if they want to fix something or extend something or add a new type of snitch, they can contribute that back, and if you get your time zones right, or you've got a big enough community, that can be fed back within a matter of hours, and a new release can be available. You want a solution that iterates in that time frame, and this gives you that. So kind of the last part of the tutorial is really meant as an open discussion, but we've seeded it with kind of some of the topics that are at the forefront of our mind, things that we're actively working on. Starting at the bottom, people have now kind of become accustomed enough to, especially some of the Nosql deployments, and that they want this type of reliability, they want this type of ease of deployment, but they actually care about it, not just getting it started, but making sure that it runs efficiently thereafter. Nobody can become an expert in all of the systems, and so our approach is to work with people who are experts in the various tools like Cassandra or MemSQL, and work with them so that we have blueprints that encapsulate a lot of the knowledge, so that for the 90% of us who just want something that works initially, we'll have that. So if any of you in the audience have particular favorites, either in the data store side or other software side, or going low level to infrastructure or operating systems, happy to open this up to questions. There are some topics on the board behind me. If any of those pique your interest, you can holler out some of those.
So as a general question then, what databases, be it NoSQL, NewSQL, traditional, are people running in production?
Shall we just run around the room, start in this corner?
I hate to say it's similar to going through the Nosql, but Microsoft SQL Server.
Postgres.
So far, no duplicates. Let's see if we can keep that going all the way around the room.
Just observe.
Okay.
H2O.
H2O. H2O. Awesome.
Also MySQL with IAD.
No duplicates. No one said that. Excellent. Any others? I love that map that we put up earlier when I came across that. It's a lot of fun. You've got to take it with a pinch of salt. But in terms of just sort of having a loose family resemblance, who's near whom, it's a great way to look at it. It is very much out of date, so I need to find out if there's a newer version, even though it's just 4 or 5 months old. A couple of the ones I've come across aren't up there. So kind of the things that is top of mind for us, some of the guys, particularly around Postgres, are building up reliable fault-tolerant pairs that are backed by block storage for that. There's been a solution for MySQL, so it's kind of porting that across to Postgres. That's one of the active areas. In order to make this work, having a good abstraction around block storage is something that is being baked. It's there for some clouds, starting to be there for a lot more. We're starting to see the same thing when it comes to private networks. Availability zones are still done in lots of different ways, and so it's a little bit harder, and so the strategies tend to be a little more specific to the applications. As we kind of move up from the very virtual infrastructure, can't believe it was called Infrastructure 3.0, I apologize for that. But when we get to managing the servers, good tie-ins, there's starting to be a plethora of systems. One of the things that impressed me about Salt is that it's making that shift away from the procedural code, writing Ruby, to being able to do a lot more in YAML to describe what should be on a machine. So it's a declarative syntax. And that kind of mirrors our philosophy, that the YAML is very new, hot off the presses. We could have put in place a YAML 2 years ago, but it would have been very bad because there's been a whole lot that we've learned about how do we most appropriately model these concepts. And so I think kind of the server management has gone through the same evolution in that 2 years ago, any declarative abstraction would have been weak. Now it's very, for the common purposes, I think often it's exactly what you want. The nice thing about those declarative representations, of course, is that not only do they make it easy for those of us who don't code or don't want to code to open it in a text editor, but they make it easy to put in place GUIs around it that let you do drag and drop, and it's just building up some type of tree data structure. Underneath it, it is generating, well, it's a config file, but it's text that can be version controlled and tracked, which is vital in this day and age. But starting to have GUIs on top of this, so you can get some really nifty design tools that let you take quite complex concepts, add in new concepts on the fly, and inherit from repositories hosted up at GitHub, for instance. Any other questions or last-minute comments? Well, thank you all for coming. We're running the developer lounge, which is back as you walk in, even before all the booths, out to the left. Many of us will be around there. We'd love to have you come by and chat some more if that's of interest. Cheers.